Okay, back. Where did we leave off? Ah, yes. Work done by variable forces. Now, we've been working with forces that were constant throughout an entire process, and that makes things easy, but it's not always the way things are. Forces often change from one place to another. They often change over time, and the path between 2 points may not be straight lines. It may be curved. So the work done by variable forces can be given by the components of the forces and the displacements along the path. So for dw, you can consider that to be the x component of the force times the x component of the infinitesimally small displacement plus the y component of the force times the infinitesimally small y component of the displacement plus the z component of the force times the infinitely small z component of the displacement. Fx, Fy, and Fz are all functions of the position on the path, and the displacement depends on the equation of the path. So that all sounds nice and convenient. So let's try doing an example like that, though, and see how that works. Work done by variable force on a curved path. When we say the path is curved, what we really mean is that there's an equation for it that's not linear. So the equation is not the equation of a straight line. So what we've got here is an object that moves along a parabolic path, the equation for which is y equals 0.5 meters to the minus 1 times x squared. And the fact that it's x squared is what makes it a parabola instead of a straight line. And the object is moving from the origin, or point A, which is 0, 0, that is x is 0 and y is 0, to point B, where x is 2 and y is 2. Under the influence of the force, this given by 5 newtons per meter times y times unit vector I, plus 10 newtons per meter times x times unit vector j. And you want to calculate the work done. Okay, so first what we have to do is notice that the components of the force are given as functions of x and y. So basically x and y, and also x and y, or x and y. And so what we want to do is basically use the path equation to find y and dy in terms of x and dx. You could do it in the other way also. You could find x and dx in terms of y and dy, but as it turns out, doing it that way gets quite a bit more complicated. And so we won't do it that way. We'll do it this way. Okay, so y is 0.5 meters to the minus 1 times x squared. That means dy, that is taking the derivative of y, would be 0.5 times 2 times x to the 2 minus 1 power. So when you're taking the derivative of a variable, remember, you basically multiply it by the exponent and then reduce the exponent by 1. So that's why we have 2 times 0.5 meters to the minus 1 times x to the 2 minus 1 power times dx, or in other words, 1 meters to the minus 1 times x dx. So that is dy in terms of x. And there's y in terms of x, which we were actually given at the beginning. The integral for work is just a definite integral of a function of x. So if we look at the infinitesimal element of work, or the infinitesimal increment of work, if you want to think of it like that, dw should be equal to fx dx plus fy dy. We don't have any z term here, so that makes it a little bit easier. Fx dx is basically, let's see, it's basically fx is, looking back here, fx is basically the X term in the force equation, which is 5 newtons per meters times Y. Okay, so that's part of Fx. It's everything except the unit vector in the X direction. So 5 newtons per meter times Y, that is Fx. Okay, so 5 Newton meters times Y times dx. Fy, again, going back to the last page, Fy is going to be the Y component of the force, everything except the unit vector J. So 10 newtons per meters times X, that's Fy. Okay, so 10 newtons per meter times X times dy. All right, so now we substitute for the Y and the X. Y we found in terms of X is actually 0.5 meters to the minus 1 times X squared. That was actually given. So remember, Y is 0.5 meters to the minus 1 times X squared. That was given originally. And so we can substitute that in for Y here. So that's what this is. That's Y, 0.5 meters to the minus 1 times X squared. That's Y. We still have Fx, or what's left of it, 5 newtons per meters. The Y we changed to this. Okay, and then dx. In the second term, we have 10 newtons per meter times x. We can leave that in terms of x because we're putting everything in terms of x. And dy, though, we had dy here. dy, as we found before, is 1 meters to the minus 1 times x dx. So 1 meters to the minus 1 x dx goes in place of dy. And then we can work it all out. So we get 2.5 newtons per meter squared. Okay, because this is newtons per meters times meters to the minus 1. So that's newtons per meter squared times x squared, because x squared, dx, plus 10 newtons per meter squared, x squared dx. So we can add these together and we just get 12.5 newtons per meter squared times x squared dx. Simple. But we're not done with the work yet. This was dw. Work is the integral of that between point A and point B. So work is going to be the integral of 12.5 newtons per meter squared times x squared dx between, since x is the variable here, 2 meters, which is the x term at point B, and 0 meters, which is the x term at the origin. And this is equal, you can take the 12.5 newtons per meter squared outside the integral because that's a constant. So it would be that times the integral of x squared dx. And when you do the integral, what you do, of course, is you divide the, or basically you raise the, you raise the exponent by 1 and also divide it by that number. So it's 12.5 newtons per meter squared over, or times 1/3 times x to the third, from values of x from 2 down to 0. Okay, 12.5 divided by 3 is 4.17. So it's 4.17 newtons per meter squared times x to the third from values of x from 2 down to 0. So we have this. Substitute 2 and substitute 0 and subtract them. 4.17 newtons per meter squared times 2 meters to the third power minus the same with 0 meters to the third power, which is of course 0. And we get 33.4 Newton meters, or 33.4 joules. Okay, so that was a bit of a challenge. It's even more of a challenge And in fact, I'm going to end up skipping it because as you can see, it gets really complicated when you try to do it the other way around, when you try to express x in terms of y. So basically, if you're doing a problem like this and you try doing it one way and it gets really complicated like it does here, with all sorts of like 1 over square root of 2 plus 2 square root of 2 and crap like that, then try doing it the other way around and you might find that it's a lot easier like it was in this case. But anyway, you can go through all of this stuff and notice that you do end up with the same answer as we got above. It's just that the bookkeeping is a lot harder. Okay, trying another example very similar to that last one. We find the work done by the force that's equal to 5 newtons per meter times y times unit vector I plus 10 newtons per meter times x times unit vector j. That's actually the same force as the last example from point A to point B, and the point A and point B are the same, but the function, the path function, is now 0.25 meters to the minus 2 times x to the third. Okay, so we have y equals 0.25 meters to the minus 2 times x to the third. That was given. That means dy must be the derivative of this, which would be 3 times 0.25 meters to the minus 2 times x squared. Okay, that is, you multiply the you multiply by the current exponent and then reduce the exponent by 1. And that's 0.75 meters to the minus 2 times x squared dx. All right, so the infinitesimal increment of work would be fx dx plus fy dy. Fx is the x term of the force equation, which again is 5 newtons per meter times y. Okay, and the x component of the force is, or sorry, the y component of the force is 10 newtons per meter times x, and dy, as we just found, is 0.75 times x squared dx. And we can also substitute in what was y. We've got y here. We can substitute in 0.25 meters to the minus 2 times x to the third. And so we end up with this 5 newtons per meters times 0.25 meters to the minus 2 x to the third dx plus 10 newtons per meter times x times 0.75 meters to the minus 2 times x squared dx. And when we work all of that out and consolidate all the terms, we end up with 5 times 0.25, that's 1.25 newtons per meter cubed, actually, because you have newtons per meter times meter to the minus 2, so that's newtons per meters cubed, times x to the third dx, plus 10 times 0.75, that's 7.5, newtons per meter cubed again, because it's newtons per meter times meters to the minus 2. So that's newtons over meters to the third, times x squared. So that's x to the third dx. So in each of these terms, you've got x to the third dx, and you just add the numbers up and you get 8.75 newtons over meters to the third times x to the third times dx. Now, all you have to do is take the derivative of that, or sorry, integral, other way, take the integral of that. Work would be the integral from point A to point B of 8.75 times x to the third dx. The 8.75 is a constant, so it can come out of the integral. So it's 8.75 times the integral from 0 to 2 of x to the third dx. That is equal to 8.75. And when you take the integral of x to the third, you raise the exponent by 1 and divide by that number also. So it's 1/4 x to the fourth. Okay. That is the integral of x to the third dx. And that would go from x values of 2 down to 0. 8.75 times 1/4 is 2.1875 newtons per cubic meter times x to the fourth from 2 down to 0. So we have 2.1875 newtons per cubic meter times 2 meters to the fourth power minus the same only with 0 meters to the fourth power, which is of course 0. So that term drops out and we get 35 Newton meters, or in other words, 35 joules. So there you go. Not too difficult. Okay. Force and kinetic energy can also be related to the idea of springs, because you exert a certain force on a spring and it compresses, and if you then let it go, it moves with a certain speed. The force that is exerted by a perfectly elastic spring is actually variable depending on how much it's compressed. And when we say a perfectly elastic spring, what we essentially mean is that any spring that obeys Hooke's law. Hooke's law is given as F equals negative kx. That is, the force on the spring is equal to the negative of what's known as k, that what's known as the spring constant, which will have units of newtons per meter. And that's just a term that relates the amount of force applied to a spring and the amount by which the length of the spring changes. So you, for the spring constant, it just tells you you apply a certain number of newtons to the spring and it changes length by 1 meter. That's basically what the spring constant tells you. If the spring constant is a large number, then you have what would be considered a really stiff spring, like maybe the spring in the suspension of a car. And if the spring constant is a small number, then you have what's known as sort of a really loose or a really weak spring, say the spring in a ballpoint pen. Let's find a pen I can actually take apart. No, not that one. Okay, let's try this one. Say, okay, that spring there. That's a very weak spring, and it's going to have a very small number for the spring constant. Okay, trying to get it back together now. Okay. And delta X is the amount by which the spring extends or compresses when the force is applied. And you can take that as basically the X coordinate if you're stretching it in the X direction. The X coordinate at its maximum deflection, either extension or compression, minus the X coordinate at its equilibrium position. That's what XEQ means. Equilibrium position is just the position where the spring is when there are no other forces being applied to it. So basically it's the position of the spring at rest. Okay. And when we look at the work done by spring force, you have to define your axes. The way the equation works implies that the spring is being stretched along the X direction. But it could be the Y direction or the Z direction, in which case delta X in this equation would become delta Y or delta Z instead. But usually we consider the spring as stretching along the X direction. And that would be in the direction of either increasing or decreasing length, depending on whether the spring is being stretched or compressed. The origin, again, is the equilibrium position. The equilibrium position is normally taken as being an X value of 0, but it doesn't necessarily have to be. Stretching or extension of the spring would be considered a positive delta X, and compression of the spring would be considered a negative delta X. And the spring force in this case, well, in any case, would only have one component, the component that's in the direction of the extension or compression. So F in that direction would be equal to negative Kx. And the work done if X goes from, say, position A to position B would be just given as the integral of fx dx from A to B. Fx, again, is negative Kx, and the K is, and the negative sign, are both constants. So you can take those outside the integral. So that would be negative K times the integral from A to B of x dx. And when you take the integral, again, you raise the exponent by 1 and divide by that number also. So that's negative K times 1/2 x squared from A to B. Or in other words, negative 1/2 K from x squared at, that is the x coordinate squared at point B, minus the x coordinate squared at point A. Okay, and then the work done by the spring or on the spring is independent of the path between A and B. And we have an example here of work done by a spring force, but actually we're kind of at the limit of what I wanted to do for this video too. So I'm going to end the third segment a little early to compensate for having the second one go long. And we'll pick up there next time with an example. We'll do a quick review of this stuff and then go on to an actual example. So until next time, see you later.